Welcome to Part 2 of Chapter 4, Chemical Bonds, the ties that bind. During Part 1 of Chapter 4, we discussed ionic bonds. During Part 2, we will discuss polyatomic ions and various naming conventions. Let's take a moment and talk about the distinction between atoms and ions. Atoms are neutral. These are uncharged versions of the elements. When we take one of these atoms and either give it an extra electron, or take from it an electron, it becomes an ion which has a charge. So ions are charged atoms. Now, ions also do not exist alone. They always come as a pair, one with a positive charge and one with a negative charge. An ionic compound is composed of a positively charged ion and a negatively charged ion. In the course of a chemical reaction, atoms are either going to gain electrons or lose electrons, or share electrons, in order to have an octet of 8 electrons, 8 valence electrons. This is known as the octet rule. Metals, or group 1 and 2 elements, are going to lose electrons to take on the electron configuration from the previous noble gas, and in doing so, they form positive ions or cations. Nonmetals, or group 7 and 8 elements, are going to gain electrons to take on the electronic configuration of the next noble gas. And in the process of doing this, they form a negative ion or an anion. As you can see here, these are the ions that some of the common elements will take. All of the group 1 elements can lose an electron to form a cation with a +1 charge. All of the group 2 elements can lose 2 electrons to form a cation with a +2 charge. And the same pattern is true for groups 7, 6, and 5. Group 7 elements will gain 1 electron to form an anion and also have their octet. Here is another example of this ionic bond forming between a potassium and a chlorine. In this example, we also have the Lewis dot structure. Potassium, which has 1 valence electron, will lose that 1 electron to form a positive charge. Chlorine, which has 7 valence electrons, will gain that 1 electron to form chlorine minus with 8 valence electrons and a negative charge. The resulting ion from an element gaining or losing an electron can be shown in Table 4.2. Hydrogen, for example, can become the hydrogen ion when it loses 1 electron, and the symbol for that will be H+. These are the symbol names for some monoatomic ions. In order for us to be able to effectively communicate which element or ion we're talking about, formulas and names can be composed for these ionic compounds. The cationic charge is the charge of a cation from one of the representative elements in the same family number. The name of a cation is simply the name of the element. So an example would be, for sodium, the ion of sodium would be the sodium ion. The ion for magnesium would be the magnesium ion. An anion has a little bit different naming schematic. The charge of an anion from the representative element is equal to the family number -8. The name of the anion is going to have a suffix. So in this case, when we take an element and convert it into an anion, we're going to add the suffix IDE to the end. So chlorine, as an ion, will become the chloride ion. Oxygen, as an ion, will become the oxide ion. Then we can combine the 2 ions to form they compound with its own binary name. The binary ionic compound will simply be the name of the two ions combined. So for example, for NaCl, sodium chloride, we take the sodium from the Na plus and the chloride from the chlorine minus and add them together to form sodium chloride. Another example, magnesium oxide, uses the name from the first element, the first ion, magnesium, and the second anion, oxide, to form magnesium oxide. There are some elements, such as transition metals, which can exhibit more than one positive ionic charge. These elements can obtain a +1 charge, a +2 charge, or even in some cases a +3 charge, and include transition metals like iron and copper. In the case of these ions, we can use Roman numerals to denote the charge of the ions involved, and then common names can be designated from the ionic charge. Polyatomic ions are groups of covalently bonded atoms with a single charge. We'll talk more about covalent bonds in a few minutes, but you can use Table 4.4 to reference some of these common polyatomic ions. For example, the ammonium ion has a symbol of a formula of NH4. This is composed of a nitrogen and 4 hydrogens, and overall, these elements are combined to have a +1 charge. A variety of different polyatomic ions are listed, with charges ranging from +1, -1, -2, and -3. When we go to write out the formulas for polyatomic ions, they're going to be a little bit more complicated. In this case, we're going to use both the name of the polyatomic ion and the name of the monoatomic ion together in order to form the formula and the name. The first example we'll look at is calcium nitrate. In this example, we use a calcium ion and a nitrate ion to form calcium nitrate. Now, we'll break this up into two parts. First, when we're going through the naming, the calcium ion is the cation, and so we use the name calcium for that ion. And then the nitrate ion is the anion. We can reference Table 4.4. If we look at the nitrate ion, here's the formula, and here's the -1 charge. So overall, we have a calcium with a +2 charge and a nitrate with a -1 charge. It's important at the end of writing out this formula for us to have a balance of charge. In this case, calcium is +2 and nitrate is -1, so that wouldn't be balanced. In order for us to balance this, we're going to need 2 nitrate ions for every calcium ion. This gives us 2 negative charges to balance out the +2 from the calcium. So when we write out the formula, it'll be calcium, and then we use parentheses to show that we're going to end up with 2 of the nitrate ions. Here's another example. This is ammonium sulfate. Here we're actually using 2 polyatomic ions. And so we start with the ammonia. Ammonia, if we reference the table, is NH4 +1, and then sulfate is SO4 2-. So we have a +1 charge on the ammonia and a 2- charge on the sulfate. When we go to write out this formula, we're going to need 2 ammonias for each sulfate because the ammonium has a +1 charge and the sulfate has a -2 charge. It'll take 2 ammoniums to balance out that sulfate charge. And then when we write out the name, it will just be ammonium sulfate. A compound which has a property of absorbing moisture from the air is considered to be hygroscopic. One example of a hygroscopic compound is magnesium sulfate. This compound is often used as a desiccant to create a low humidity environment.